Um, so another thank you also for inviting me to be here. It's a great honor to be here and present my work and to see what people are doing here in the department. I also would like to thank the Department of Atmospheric Sciences or the Institute or the Center of Atmospheric Sciences for hosting this event and allowing me to be here, and then also people behind the scenes and Yvonne for organizing all this and making sure our stay is smooth. So before I start, I would like to acknowledge a few people who contributed to this research, or rather who did the research, because they're actually in the lab in the field. So some former and present PhD students, Yvonne Bose, Alex Beck, they're former PhD students, and then current students are Rob David and Stefan Münch, whose results I'm going to present here, and then also a former PhD student who's also a group leader at ETH, Jan Henneberger. And we have a really awesome technician called Hannes Wiedler, and he really ensures that our research goes smoothly by keeping our instruments working and functioning. So I'll be talking about aerosol particles as ice crystal seeds in the troposphere, so I'll be focusing mostly in the mid to upper troposphere regime. And I'll try and make the connection between the nanoscale and the cloud scale. And when I gave this title a long time ago, as I'm sure most speakers did, but when I started preparing the talk, I realized I can't start from nanopores and go to clouds. I really needed to go the other way around, start from clouds and come down to nanopores, and then maybe go back to clouds. So that's what we'll do. So just as a motivation, a very frequently used figure from the IPCC report in 2013 about forcing agents that contribute to climate change. And so this is specifically for radiative forcing, relevant for time periods, compared to time periods before 1750. So what I would like to draw your attention to, which pertains to the research we are doing, is aerosol cloud interaction. So you see that bar right there. So if you compare the confidence level or the level of understanding to all the other forcing agents, you see that for aerosol cloud interactions, that's low. We know we have a cooling effect, and that's indicated by the blue bar. But then you also see that the error bar, or the uncertainty associated with that result, is also the largest compared to any other forcing agents. And so really what we say is that we don't know much about aerosol cloud interactions. We have a low level of understanding and a high uncertainty. So if we improve our understanding of this process or this interaction, then we can hopefully work to reduce the uncertainty. And so I'll just start by giving a background of how aerosol cloud interactions affect radiative forcing. So I'm going to start with liquid phase clouds first. And so what you see here is two scenarios where you have a clean cloud and a polluted cloud. So by clean, we mean fewer aerosol particles and a smaller number of droplets. And by polluted, I mean a higher number of aerosol particles, which leads to a cloud with a higher number of droplets. In the first case, because you have a clean cloud, you'll have fewer droplets that will be larger in size. And in the second case, you have a polluted cloud, so you'll have more droplets, but they'll be smaller in size. So the difference between the two is that you'll reflect more solar radiation in the polluted cloud because you'll have a high reflectivity. You'll have a high reflectivity. So you will reflect more radiation back to outer space, whereas in the clean cloud, you'll reflect less of this radiation. Also, because you have larger droplets in the clean cloud compared to the polluted cloud, you may have early onset of precipitation in the clean cloud. But in the polluted cloud, you have many small droplets, so you'll delay the onset of precipitation because collision coalescence processes will take a longer time in this case. So you may have delayed precipitation, but it may be stronger. So what happens to this scenario when you add ice crystals into the mix? So you have the same situation again, a clean cloud and a polluted cloud. Same scenario, more aerosols in the polluted cloud, so you have smaller cloud droplets, but now you have ice crystals in there because you've reached levels that allow freezing to occur. So in the case of the polluted cloud, you'll have smaller droplets, so you'll have delayed freezing, but freezing will occur at higher altitudes because you need to reach colder temperatures because of the smaller droplets. And therefore, you'll have a larger vertical extent of the cloud. But again, the outcome is the same. You'll have a delayed but stronger precipitation event from this polluted cloud because you have smaller droplets and smaller ice crystals compared to the clean cloud. So in general, what we know is that if you have high clouds, so ice clouds, they would tend to warm the Earth's atmosphere because they trap long-wave radiation. And if you have low clouds, which are mostly liquid phase clouds, these tend to be optically thick, so they should cool the Earth's atmosphere because they block incoming solar radiation. But then the question becomes, what happens when you have a mixed phase cloud like this, where you have liquid droplets and ice crystals in there? And they're mid-level clouds, typically. And this really depends on the longevity of the cloud and the microphysical composition. And by that, I mean, what is the ratio of ice crystals to water droplets in the cloud? So that's definitely one motivation for focusing on aerosol cloud interactions. But other motivations for focusing specifically on ice is that it introduces a lot of complexity to the cloud systems. So first, we know that the water vapor budget in the upper troposphere is very important because especially in that location, it's a very active greenhouse gas. And so it's a very active greenhouse gas. And so if we can predict the amount of ice condensate in the upper troposphere, then we can also predict what the budget of water vapor is. Precipitation formation, as we saw in the previous slides, is also influenced by the ice phase because ice crystals tend to be larger than water droplets, and I'll address that on the next slides. They tend to be involved almost always when we receive precipitation on Earth. And so that, in turn, plays into the lifetime of a cloud, so how long a cloud will last. And that also determines the albedo of the Earth in general because of the lifetime of the cloud. Ice crystal number concentrations will also affect the albedo of the cloud because whether you have water droplets or ice crystals will affect the reflectivity of the cloud. So those are main motivations, excuse me. So the other reasons to understand cloud formation processes in general, not only ice nucleation, is that you want to prevent damage, for example, from hail or graupel formation, and to understand when these events would affect us down here on the ground, and also aviation hazards. So we need to be able to predict when you have supercool liquid in the atmosphere. If you all remember the Air France flight from Rio de Janeiro to Paris, I think it was in the 90s, really the main reason for the crash was flying into a mixed phase cloud system where you had supercooled liquid droplets. So we would like to prevent the damage, and then of course, if we understand this system much better, we can also engineer the climate. And I would like to believe most people here don't agree with that, but if we were to do that, then we need to understand these processes very well. And so part of the complexity in understanding this whole system is that we really have to understand science over scale. So you can start from the molecular scale and go all the way to the cloud scale. And this is covering a huge range of scales. And also covering a huge range of disciplines. So you need to understand molecular dynamics, surface science, nucleation processes, and cloud microphysics to be able to actually understand how droplets and crystals form in the atmosphere. So let me take you through this a little bit. So we know that we can form a new phase, be it a droplet or an ice crystal phase, by water molecules coming together to form clusters, and the clusters could grow eventually to become a critical size. And either they grow in one phase or they attach themselves to a surface. So you have an interface that stabilizes the clusters. And then you can nucleate a new phase here. And the new phase could be water droplets or ice crystals in this case, then get incorporated into a larger system, and you have your cloud. So the processes that lead to this cloud formation eventually is what we would like to understand more. But in order to get there, we need to understand this part. And the surfaces here that could influence this nucleation process could be of a large variety in the atmosphere. As we know, it's a very complex composition. So there are some images here I've put down there. So this is mineral dust, for instance. These are pollen particles. Here you have other type of fungal spores, and here you have crystalline salts from inorganic compounds. And so really, we don't really know what happens in this black box, that I like to call it. Maybe we're beginning to understand a little bit about this nucleation process, but then we really don't know what happens once we form these like micro-sized ice crystals into the cloud system. So that's what we'll try and focus on. So I know you have meteorologists and chemists and physicists in the audience, but I just want to go over the definition for relative humidity because I'll be using it a lot. But more importantly, relative humidity with respect to ice. So with respect to water, we have your standard formula, partial pressure of water divided by the equilibrium vapor pressure of water, and expressed as a percentage. I also use relative humidity with respect to ice a lot in the work we're presenting. And that's identical to RHW, but it's basically normalized to the vapor pressure with respect to an ice surface. And so the prime difference over here is that the equilibrium vapor pressure with respect to an ice surface is lower than that with respect to a water surface. And so what this means is that at any given temperature, the relative humidity with respect to ice is always greater than that with respect to water. So this means that if in the same environment you have ice crystals and water drops, that ice crystals will always grow larger than water drops. And if they coexist, then ice can also grow at the expense of water droplets. So ice crystals can continue growing and water droplets can continue evaporating. And so this is known as the Bergeron-Findeisen process. So with that in mind, I'll come to the ice nucleation mechanisms that are relevant for the atmosphere. So I'll represent an aerosol particle, which we also call an ice nucleating particle. So keep this acronym in mind, INP, you'll see it a lot. And so that's an aerosol particle in the solid state, or an aerosol particle that can provide a surface. We have a liquid droplet in an ice crystal. So first, we have homogeneous freezing. And as the name suggests, homogeneous, so it's one phase. So you have an aqueous droplet here that, when reaching sufficient supercooling, so in this case -38, and high enough relative humidity, will spontaneously freeze to form an ice crystal. So you just have one phase involved here. There is no foreign substrate. But then you can have heterogeneous freezing. And as the title suggests, heterogeneous meaning you have more than one. So here you have your aerosol particle, which we call an INP, involved. And so the first heterogeneous mechanism is immersion freezing or condensation freezing. We treat that as the same here. It should occur when you have high relative humidity, so close to 100% or higher. And so that occurs when you have an aerosol particle or an INP that's submerged in a water layer or a water droplet. And the surface of the particle acts as a template for ice to form, or a critical ice nucleus to form. And then eventually you have nucleation, and then you have growth of the bulk ice crystal. Then you can have ice nucleation by deposition. And this should occur at relative humidities with respect to water of less than 100%, because we're not invoking the liquid phase over here. But RHI has to be higher than 100% because you need to have favorable conditions for ice to form. So basically here you just have the aerosol surface acting as a template for a critical cluster, and you form an ice crystal directly from the vapor phase. So the liquid phase is escaped here. And hence we call it deposition. And then lastly we have contact nucleation, where similar to immersion, you have a liquid droplet that exists, but an aerosol particle colliding with the liquid droplet. And this is a type of process that can occur in mixed phase clouds. And then at the point of collision, you have the same formulation as here. So you have the surface acting as a critical cluster template. So you can form your critical ice cluster, and then you have an ice crystal forming. Now, immersion and contact are very relevant for mixed phase clouds, as you can imagine, because they involve the liquid phase. I'll talk mostly about, actually only about immersion and deposition nucleation today. I wouldn't dare talk about contact nucleation because we have an expert in the audience right here. And Luis published a lot of very important and interesting research on contact nucleation because it's very poorly understood. So if you're interested in knowing more about that process, you can talk to Luis. And so let's look at how these two processes, homogeneous and heterogeneous ice nucleation, could affect cloud properties, right? And so here I have sort of a schematic. So this is sort of ground level, or you can assume boundary layer. And so as you travel up in the atmosphere, your relative humidity is increasing and your temperature is decreasing, so you get colder. So say you have some aerosol particles in the liquid phase. In a rising air parcel, these would rise up, they would get colder and increase the relative humidity. Eventually, they'd reach conditions that are favorable for freezing, homogeneous freezing, and you'd have cirrus clouds or ice crystals, ice phase clouds. So you have all these solution droplets freezing to form ice crystals. Then imagine another scenario where you have a mixture of particles, like in the atmosphere. So you have some solid particles, some liquid particles. Some of these could be ice nucleating particles. And so if this parcel starts to rise, because you have some ice nucleating particles, and say you reach a threshold that's favorable for heterogeneous ice nucleation, you'll form a few ice crystals only on those solid particles. But the liquid particles still remain liquid because you've not reached these conditions, so you can't freeze them. So you'll form few ice crystals, but because you have this available liquid there, these ice crystals can grow larger. So when this parcel continues to rise and forms a pure ice cloud, what happens is you have much fewer crystals than the homogeneously frozen cloud, but they're larger. And so this means that this cloud could precipitate faster, but it will also have different optical and radiative properties compared to that cloud. So these are how the two processes can affect clouds. So in the atmosphere, we have different aerosol species. And this is, I would say, a rather simplified picture and just a general categorization of kind of species in the atmosphere. What I would like to point your attention to is that this orange-red region. So you have these dust regions in the Earth. And so Asian desert, Arabian desert, Sahara desert, which is a huge source of dust. And this dust, as you can tell from this image, makes it quite far from its source. So you can see Australian desert dust here, but here you see Saharan dust can actually be transported across the Atlantic and can also reach Mexico, or the Yucatan rather. And this reaches Florida, it reaches the northwest United States. So there's a lot of impacts of this dust that is being transported to a very far distance. And so we're going to focus a little bit on the cloud-forming properties of this dust. But the question becomes that when you have so many different types of components in the atmosphere, sulfates, dust, soluble material, insoluble material, organics, what you don't see here is you have also biological particles, which can't be distinguished by the satellite images. The question becomes, what's the role of all these different species on ice cloud formation? So I wouldn't really talk about that in detail today, but I'll just take you over a quick overview, because as you can see, a lot of studies have been done in the past on this. So some of the factors that promote ice nucleation are very similar to warm cloud, to CCN activation. And so size is one of the physical effects that is very important. So the larger your particle is, the better it is as an ice nucleating particle. It's more effective at forming ice. And there's a lot of studies, in particular the one of Archuleta was one of the first ones to show this very categorically in the lab. Composition, which relates to the previous slide. So how does particle composition influence ice cloud formation? In general, I like to make this category where I say biological particles are the most efficient, followed by dust particles, organics, and then black carbon or soot particles are the least efficient for forming ice heterogeneously. And so the reason I say this is because biological particles can freeze at fairly moderate supercoolings as warm as -2, as I've heard from Luis recently in his latest field work. But what we need to be careful about here is that we can make this categorization, but in order to make it atmospherically relevant, what we need to understand is how much of biological particles actually exist in the atmosphere compared to dust and organics. So that becomes an interplay between what's relevant in the lab versus what's present in the atmosphere. I put marine in both categories because you can have marine particles you can have biological particles that come from the marine ecosystem, and you can also have organics that come from the marine ecosystem. So they sort of fall in both categories. And actually, Luis was involved in a study in 2015, and it was one of the first studies to show directly with field work that marine particles were quite active. Marine ambient particles were quite active at forming ice clouds. There are other studies here, also one done by my student that also showed this and detected marine-influenced air masses in situ much later on, and mostly motivated by the study that Luis published. And then we have what we call an active site requirement. So the surface that stabilizes a critical ice cluster. Why is that surface able to stabilize a critical ice cluster? Is it because there's some chemical functional group that attracts a water molecule? Is it because you have a high energy crystal plane that has steps or corners or cracks or pores? we don't really know the exact identity of an active site, but what we do know is that when you have these kinds of features, they do promote ice nucleation. But we don't know exactly which one of these features is actually responsible. And most likely it's a combination of these features that's responsible. And then there's studies to suggest that if the crystal lattice of your surface, your ice nucleating particle, your aerosol, matches that of ice, it would form a good template for ice to form upon that. And a lot of studies have shown graphite, dust, and silver iodide, which have similar hexagonal structures to hexagonal ice, promote ice nucleation. And these are some of molecular dynamic simulations rather than empirical studies that show that even graphite, which should be rather hydrophobic, can promote ice nucleation because of the crystal lattice match. And lastly, I'll talk about the insolubility requirement, which is you need a surface. You need an interface or a surface where a critical ice germ can form. If you don't have a surface or you don't have an interface, then you don't have this ability. And so in the past, this was referred to as the insolubility requirement, but then this was challenged by the notion of biological particles that are soluble, can induce heterogeneous nucleation, but also inorganic salts like ammonium sulfate and some other inorganic salts who are also shown to be active heterogeneous ice nuclei. So I would change this and say instead of the insolubility requirement, it's an interfacial requirement, would be more accurate. Okay, so with that, the take-home message really from this is no surprise, is that chemistry and physics are both important for ice nucleation, composition and morphology, basically. And so the jury is still out on which one is more important, but I'm leaning more towards morphology or physics. Okay, so in this talk, I'm going to focus on two cloud regimes, as I said, in the mid to upper troposphere. So let me orient you with this figure. So we have saturation ratio with respect to ice on the y-axis. So this is akin or very similar to RHI, basically, expressed as a ratio rather than a percentage. So that 1 would be 100% relative humidity with respect to ice, and 1.8 would be 180% RHI. On the y-axis, we have, on the x-axis, we have temperature. And then we have this diagonal line here that is labeled as water saturation. So above this line, so in this space here, your relative humidity with respect to water is higher than 100%. Below this line, you're subsaturated with respect to water. Then this vertical line here is a threshold for homogeneous freezing, as we saw earlier, so minus 38. So when you're on the right-hand side of this plot, what you have is the regime that's favorable for mixed phase clouds, because you can have supercooled liquid droplets that can exist here. And when you're in this regime here, you're in the regime for ice cloud formation, because you have mostly ice crystals existing here. You don't have any liquid droplets. Because once you cross this barrier here, even a liquid droplet that's pure liquid or pure water will freeze, even in the absence of a surface or interfacial surface. So in the absence of an ice nucleating particle. So the mechanisms that we talked about, immersion freezing, are relevant along this line here, where you have liquid droplets that can exist. And then we talked about deposition nucleation, which can take place at conditions that are subsaturated with respect to water, but supersaturated with respect to ice. But you can also have deposition nucleation taking place in the mixed phase cloud regime, if you have favorable conditions. And that, again, has to be in this region here, where you're below water saturation. So just to keep in mind. Now, if you recall, deposition was termed as nucleation from the vapor phase directly to the solid phase. But that is really against the Ostwald's rule of stages, because that states that when you have a phase transition, you should go to the stage that's energetically as close to the parent phase. So really, Ostwald's rule of stages would suggest that you should move to the liquid phase rather than to the ice phase. So the question becomes, is deposition nucleation real, or is liquid water still involved in deposition nucleation, and that we're just missing this? And so one of the motivations behind this question came from a study from one of my former PhD students, where he studied ice nucleation on dust particles in the lab. So I'll take you through this plot. So we have RHI on the y-axis and temperature on the x-axis, very similar to the previous plot. This diagonal line here is water saturation, and this vertical line is homogeneous freezing threshold. So what you see here is is percentage of ice formation on kaolinite dust particles. So kaolinite is a type of a clay. So the lower, the cooler colors, the blue colors, basically indicate a really low percentage of ice formation, and the red colors indicate a high percentage of ice formation. So if you're in the reds, then you have really high potential for forming ice. And what you see here is that this should all be in the deposition mode here, because this is all subsaturated with respect to water. Water saturation is only experienced above there. But even though you should technically have no liquid water, there's this sharp transition right here at the homogeneous freezing threshold. So because of this sharp transition in the activated fraction, in this percentage here, we began to wonder, if it's only the vapor phase involved, then why do we see this sharp transition at the homogeneous freezing threshold at these conditions that are supposed to be dry with respect to liquid water? So we wondered that, could it be possible that we have liquid phase water even at conditions below 100% relative humidity? So that led us, a colleague of mine, Claudia Marcoli, to then postulate this mechanism called pore condensation and freezing. And so what this is it's a means to allow water uptake at low relative humidities. So even though you're not saturated with respect to water, you can still take up water. So consider a pore, a capillary. So say, a couple nanometers wide. You always have adsorbed gas phase water on all surfaces. We know this. Even on this desk here, we'd have adsorbed gas phase water. So at low relative humidities, you have some gas phase molecules adsorbed to surfaces. You increase the relative humidity, you start to increase the adsorption of water vapor onto these surfaces. And then, further increasing this, this relative humidity, or that should read a little bit higher, will mean that this pore starts to fill up with water. And so this occurs at relative humidities lower than 100%. And so it means that if you have such pores or capillaries in atmospheric particles, it is possible that liquid water will start accumulating in these particles in the capillaries. So what that means is that if you have a porous particle and the pore fills with water at dry conditions, then if your temperature is cold enough, you could form ice in the pore, and eventually the ice can grow out of the pore, and you can get your ice crystal. So that, in fact, this ice crystal formation is not from the vapor phase, and in fact is from the liquid phase, as we would expect. Of course, if you observe this taking place above -40, then it means that one of these surfaces may have an active site that was able to nucleate this ice germ. But that's a different story. So the way we can predict this is with the inverse Kelvin effect. And basically what that tells you, we can ignore all these variables here, but this is the vapor pressure of water on a concave liquid surface, so a liquid surface that's curved this way. And it's basically a fraction, or it's a function of the vapor pressure or a flat water surface. So it's reduced by a certain amount. And this reduction is what allows water to condense at this reduced relative humidity with respect to ice. So this means that pore water, if formed, can freeze homogeneously when you're below -38, and it could freeze heterogeneously with the help of the surface of the particle if you're above -38. So with that, I'll go to two research questions that I'll address here. One is deposition nucleation real? And two is, can we predict the ice crystal number concentrations from the ice nucleating particle concentrations that we measure? And so this will take me with, will make me address two themes in the presentation. One is a laboratory theme, where we'll address the pore condensation freezing with artificial silica particles. And the other one is then to investigate what this effect would have in a global climate model. And then the second part would be the field observations, where we'll try and quantify the ice nucleating particle concentration in the atmosphere, and then see if we can, using the field measurements, if we can predict these numbers using existing parameterizations. Because the goal here is to understand or to quantify how much ice is formed in the atmosphere. And so we want to see how well we can predict this. And then we would like to compare the predicted ice nucleating particle concentrations to the observed ice crystal number concentrations in the atmosphere, because at the end goal is to understand or to know how much ice we form in the atmosphere. So with that, I'll go to our methods that we use in the lab and in the field. So we use cloud chambers or ice nucleation chambers, and we have a few different types in the lab, but mostly for the work presented here, we've used these two, zinc and pink. So zinc stands for xeric ice nucleation chamber, and pink is an identical version to zinc, and it stands for the portable ice nucleation chamber. And so the concept of these chambers is as follows. So you have particles that are so dried aerosol that you can sample from the atmosphere or from the lab that you sample into the chamber. So you can feed them into a chamber, and the concept behind the chamber is that we can carefully control the relative humidity and the temperature that the particles are exposed to in the chamber. And how we do that, I'll come to on the next slide. So we feed these particles into the chamber. Because we can control the relative humidity and the temperature in the chamber, we can activate these particles either into cloud droplets or into ice crystals. So both can form depending on the conditions you select in the chamber. These particles have some time to nucleate and to grow to larger crystals and eventually travel down the chamber towards a detection system. But before doing so, they pass this region called an evaporation section. In the evaporation section, what we do is we make sure that the relative humidity with respect to ice is at 100%, and the relative humidity with respect to water is much below 100%. So if you formed a droplet above here, it will evaporate in this section. And then eventually these particles are detected by an optical particle counter, the OPC. And the reason we need to evaporate these droplets is because we just use a size threshold to count our ice crystals. So for each ice crystal that we count, we say it's one ice nucleating particle. So basically, we assume that the ice crystal forms on a single particle, which is a fair assumption in this case. So all crystals that grow to sizes of 3 microns or larger are counted as an ice crystal, so as an INP. So for these chamber conditions, what we say is that if we set the chamber to an RHW less than 100%, we're measuring deposition nucleation mechanisms. And if we are above 100%, then we say we are measuring immersion freezing. So that's how we distinguish the two mechanisms. So how do we maintain this relative humidity, or how do we generate relative humidity and supersaturations in the chamber? So remember, if you go back, we have two walls of the chamber. We have this red wall and this blue wall. So this is a warm wall and a cold wall. So we come back here. So this is our cold wall, and this is our warm wall here. So these walls in the chamber are coated with ice as a source of water vapor. And we maintain them at two different temperatures. So in this case, we have 213 Kelvin and 233 Kelvin. So minus 40 and minus 60. So because we have them at different temperatures, we have this temperature gradient, as shown by the black line here. And we also have a gradient in partial pressure with respect to water. And that's linear because we set the two wall temperatures at these. We actively control that. But as most of you probably know, that the equilibrium vapor pressure function as a function of temperature is nonlinear for both water and ice. So this is given by this solid red line here for water, and for ice by this blue line here. So that's the equilibrium vapor pressure with respect to ice and water. And because these are nonlinear functions and we generate a linear partial pressure gradient, what happens is that at some region between the two walls, between the warm and the cold, we generate a region of supersaturation. So this solid black line here represents a saturation ratio of 1. So this is your RHI, basically. So at all conditions and all positions in the chamber, you are supersaturated with respect to ice. But when you increase your temperature difference, then for some conditions, you can also be supersaturated with respect to water. So that's shown by this blue dashed line here, where you're supersaturated with respect to ice. And in some parts of the chamber, you can also be supersaturated with respect to water. So you can create an RHW that's higher than 100% with respect to water. And we inject our sample roughly in the center. So then we know how wide our sample width is, and we know exactly, based on this calculation, what relative humidities our aerosols were exposed to. So in this case, it would be roughly 105% with respect to water, and about 170 to 80% with respect to ice. So what can we measure from these kind of experiments? The first is activated fraction. And this is basically the number of ice nucleating particles that we detect in the OPC at the bottom, divided by the number of particles that we feed into the chamber. So that just tells you the proportion of particles that form ice crystals. And then, since you know this is just based on particle numbers, but as you saw, that there is a size effect with ice nucleation. And so, if you have particles of different sizes here, then the activated fraction is not the best measure. And so what we do is we normalize this activated fraction here to the total surface area of the particles that we measure. And that basically allows us to get rid of the size effect and compare our measurements. And so that's the formulation, and what we call this the NS, or the ice nucleation active site density. But you can just keep NS in mind for now. And so basically, the higher the activated fraction is, the more efficient your particles are at forming ice. The higher your NS is, the more efficient your aerosol particles are at forming ice. And in the field, because ice nuclei or ice nucleating particles are so rare, we have really low activated fraction. So we can simplify this formula to just make it into the number of ice crystals divided by the total surface area. And this is valid only for really small activated fractions, but that's perfectly fine for the field because that's the regime we work in. So this formulation of NS assumes that temperature is more important than time, and also the particle composition is uniform across sizes, which in some cases that's not true, but in the cases we'll show, it's a fairly good assumption. So how much time do I have left? How long has it been? I have 10 minutes left. Oh, okay. So I'm going too slow. Okay, so then coming to the lab experiments with synthesized porous silica. So what we did here is collaborated with people at the Applied Sciences University, and they synthesized silica particles for us. But the reason we did this is because they can generate pores in the particles, which is what we were interested in to test the pore condensation freezing theory. And so of a very narrow size distribution. So in this case, we're showing these uniform spherical particles of amorphous silica, and we have a pore size here of roughly 2.8 nanometers plus or minus 0.2 nanometers or so. So we have these particles, and we subjected them to some experiments. So here we have the activated fraction on the y-axis and relative humidity with respect to water on the x-axis. And so if you see this number going up, it means you're forming ice, or your particles are efficient at forming ice. So we tested two particle types, the porous particles, which is the 2.8 nanometer pores, and the non-porous particles. Now, remember with the inverse Kelvin effect, we can predict at what relative humidity the pores can be full. And what we see is that for the 2.8 nanometer pores, right at this dashed line, we can calculate that the pores of this size would be full. And we see that ice formation starts exactly at that dashed line in the porous particles. So that's suggesting that that's freezing of liquid water that's been taken up into the porous particles. For the non-porous particles, I've put this in quotation marks because we expect this to be right here at 100%. So the question is, why is it still at subsaturated conditions? So is this still deposition nucleation? So I'll come to that in a second. But what's really remarkable here is that you can predict this ice nucleation very well from experiments just by this theoretical approach of the inverse Kelvin effect. And you can see that the delay between the porous and the non-porous is almost 15% relative humidity. And so that's quite significant for ice forming in the atmosphere or in clouds. Now, in the non-porous case, because these particles are synthesized, we weren't able to synthesize at the nanometer scale a perfectly smooth surface. So that just wasn't possible, no matter how much we tried. And so what we think is happening here is that even the non-porous particles have some surface features, some cavities or depressions on there. And some of these probably get filled up with liquid water. And therefore, we still have some deposition or pore condensation freezing. And so this basically says that because we're at these cold temperatures, that we probably have homogeneous freezing of pore water, and that this theory of ice nucleation could be very relevant. So to further test this and make sure that we understand what we see is we did experiments at warmer temperatures where homogeneous freezing cannot take place. and this is minus 35. And we see, so this is all background signal, and what we see is that for porous and non-porous particles, you have absolutely no ice nucleation in this warmer temperature regime. So that's telling you that you're not able, that even if you take up pore water, you can't freeze it because you're at these warm temperatures, but that actually these particles are not heterogeneous ice nucleating particles. They're only capable of forming ice at these very cold conditions. So there is no heterogeneous ice nucleation here. So what we did is we then parameterized these pore condensation freezing. So if you remember, we did these on silica particles, which are synthetic. And so we did experiments at all different conditions and came up with a function of activated fraction as a function of RH with different sizes, different pore sizes. And we tried to parameterize this into the global model. So what we did for this is we generated this red or dark red curve as you see over here. And in the atmosphere, of course, silica particles are not relevant because these are artificial. But what is relevant is illite particles, which is a clay. And illite particles are known to be composed of roughly 50 to 60% of atmospheric dust. It's a component of Saharan dust. And they're also known to be porous. So we did the same experiments, as you can see with these orange diamonds, with the illite particles. And as you see, lo and behold, they follow the same line as the silica particles. So what we did is we used the pore condensation freezing results to parameterize the first 50% or 60% of the frozen fraction or the activated fraction. And then for the remainder, we just use the non-porous particles to make it more atmospherically relevant. So we say about 60% of atmospheric dust is composed of porous material, and then the other 40% is non-porous. Then we put this parameterization into the climate model to see how this affects ice crystal formation. So these green lines here are the old parameterization that the climate model used to use, and then we have condensed this into just one new parameterization. So what you see here is the results from the climate model. So here you have the altitude, and this is the zonal means, and the latitude over here. And I would point your attention to this figure, which is more important. And this is the difference between the old parameterization and the new parameterization. And the hashed regions here are insignificant changes, but the red regions that you see here are very significant changes. So that goes up to 1,000% is the highest, and that's 0% is the lowest. So what you see in most cases, you have at least 500% difference at lower altitudes. So that's telling you that if you use the old parameterization, you're under-predicting the ice crystal number concentrations in the climate model, in your cirrus clouds, compared to when you use the new parameterization. And so that's important for cloud optical and radiative properties, as you can tell. And these differences are mostly at the lower altitudes, and the warmer temperatures, because this becomes effective right at minus 40. So this takes me now to the field studies to see if we can predict ice nucleating particle number, or ice nucleating particle numbers and ice crystal number concentrations. So we went to Tenerife, which is off the west coast of Africa, to be able to sample Saharan dust particles. And the reason we went there is pretty obvious. You're immediately west of the Sahara. You have the Saharan air layer coming here through the summer, and this air layer eventually makes its way to North America and Mexico. And so this is a picture taken from Tenerife. And so the observatory where we did our measurements is located in Izania, about 2,400 meters above sea level. And this is where the Saharan air layer comes through. So it's a hot, dry, and stable air mass. So the question becomes, why are you interested in studying ice nucleation in this dry, stable air mass? But because of the long-range transport that occurs of this dust to regions where cloud formation is relevant, that's why we're interested. Also, a lot of previous studies had suggested that dust is associated with precipitation formation. Ice crystal numbers increased in clouds when dust was present, and a lot of modelers who suggested that we don't know enough about the ice nucleating particle numbers in the Saharan air layer. So these were some motivations. But also, as you know, atmospheric dust can be quite a high burden in the troposphere, and they have long residence times, these dust particles. So they can influence really processes far away from the source. So this was a study conducted by one of my former PhD students, Yvonne Bose, and that's whose work I'll be presenting. But here is a satellite image where you can see dust of the Sahara is making its way across the Atlantic and crossing the Canary Islands and the Tenerife. And so I may skip this in the interest of time, but this is just basically a setup of how we measure the ice nucleation particles, which we sort of went through earlier. So just to the, we had conducted 2 field campaigns. I'll go through the results from 2014. So we have 4 panels here. In the first panel, so I mean, we have the time or the day of the month on the x-axis, and on the y-axis we have different things. On the first panel, we have the INP concentration. On the second panel, we have the PM, the particulate mass, PM10 concentration. In the third panel, we have the aerosol particle number concentration, but only for the large particles, between 0.5 to 1 microns. And on the fourth panel, we have the total aerosol number concentration. So we have even the small particles in blue and the large particles. What you see is different color shadings here. So let's focus on the first one, which is the green one, which we call BB1, which is a biomass burning event that occurred in Canada, and the transport made its way through to Tenerife. And what we see over there is we had very low ice nucleating particle numbers, so almost none. The PM mass, PM10, was quite low, but you have really high particle number concentrations, especially in the region below 0.5 microns. And so you have these high numbers, but you have no INP concentration. So that's one thing to say, is that the biomass burning event did not contribute much to the INP numbers. Then we have these ISDEs and MSDEs. So let's take the yellow ones, the bright yellow ones. So they are major dust events and intermediate dust events. And SDE stands for Sahara dust event. What you see here is that when you have these major dust events, so take the bright yellow, you have this huge increase in PM10 mass, as demonstrated by this increase over here. You have also this huge increase in the particle numbers in the large particle size bins, as is demonstrated here. But you also have this concurrent increase in the ice nucleating particle number. So that's telling you that when you have these major dust events, MSD1 and MSD2, that you also have an increase in the ice nucleating particle number. So it's a correlation suggesting that the ice nucleating particles are the dust particles. And then you have the same thing for the intermediate ones here, and you have the same increases. And so what we experienced there was these 2 major dust events and some intermediate ones. We had this biomass burning event. But what you also see is that you have a diurnal cycle of aerosol particle number, as would be expected in such field sites during times where you did not have any Saharan dust going through. So classifying this by events, so non-Sahara dust events, biomass in the green, and then the major and intermediate dust events in the other colors. We have your concentration of INPs on the Y and your relative humidity. So we did the same type of experiments in the field. And what you see is as you approach these higher relative humidities, you have an increase in your INP number, which is expected. But what this tells you is that your major dust events were dominating. And this could just merely be because you have more particles present. And so that's not very exciting. But to get rid of the particle number in the surface area issue, we normalize this to the NS that we talked about earlier. So we now normalize to the surface area so we can get rid of the influence of the absolute number of particles. And what we see is that all the dust events more or less collapse into within a factor of 2 to 5. And then you have these periods of non-dust and these biomass. And you can see the NS for the biomass burning event is quite low, suggesting that biomass burning particles do not affect a lot of ice formation. And so most of the difference in the INP concentration that we saw over here can be explained by just normalizing by the aerosol number and the size by accounting for the surface area. So again, the number and the size are more important in this case. But we looked at some chemistry. And so first, just to show you that we measured at 2 conditions, but I'm just going to pay attention to the top row here in the interest of time. So we have INP number on the y-axis and dust on the x-axis. And you see there's a fairly nice correlation between the two, that when you have high dust amounts, you have also high INP particle numbers. Then we looked at the amount of nitrate in our dust samples or our PM samples. And we saw some correlation for the measurements in 2014, but not much for 2013. And again, this is for the immersion freezing, and this is for the deposition nucleation. And then we looked at ammonium sulfate as well, and we saw this correlation, not very strong, but we saw a correlation when we looked at the INP versus the sulfate from ammonium, or the ammoniated sulfate, and you get this, about 40% of the data could be explained by this. So implying that when you have more of these pollutants, you have more favorable conditions for ice nucleating particles. So then we took this one step further. So these are the sort of conclusions from this, that you have more pollutants, you probably have higher solubility of the particles, so you favor this liquid phase ice nucleating process. But we took this one step further and we said, okay, but it could be that the large particles carry more pollutants or more ammonium sulfate or more nitrate. So let's normalize this to the large particle number to get rid of that effect. And then we saw that the correlation got even better with ammonium sulfate. So when your ratio of ammonium sulfate to aluminum, and that's just to normalize to dust, is between 0 and 1, you have this really nice correlation that can explain about 70% of the results there. The circles are, or the red points are dust events, and the blue points are marine events. And you can see that this doesn't really work very well for the times when we had air masses from the marine. Now these three triangles here are outliers, and the question is, why doesn't this work? So you can see that the ratio for all these three triangles of ammonium sulfate to the dust is quite high. So this would imply that you have really large amounts of ammonium sulfate per dust particle. And maybe at this point, the amount of solute material is too high, and so you're getting freezing point depression, which reduces the ice nucleating activity of these particles. But if you're below this threshold of 1, this is not enough data to put a threshold there, but that's what we're thinking, is that that's enough to promote ice nucleation. So it means that ammonium sulfate somehow is promoting ice nucleation on these dust particles. So then we came to using an existing parameterization that was published by Demotte et al. To see if we can use this parameterization here, which is based predominantly on the number of aerosol particles larger than 0.5 microns, to see if we can predict our field data that we collected in Isania. And what we see there is that it does a fairly good job. So this is the predicted INP concentration from our field data versus the observed that we observe at Isania. So what we see is that within a factor of 5, so this is 1 to 2, this is 1 to 5, that most of the data are captured quite well. And so I would say this does fairly well. In our business, up to a factor of 10 is acceptable. And so if we put a factor of 10 line here, everything would be captured. But because we were close to the Sahara, we had rather fresh dust, we like to think, except that's not entirely true as demonstrated by the ammonium sulfate. But the Demotte parameterization is based on field studies where dust was sampled a long way away from the source, so on aged particles. So what this then implies is that the ice nucleating particle concentrations that we measured at the field site may not change so much with aging or with long-term aging. And so with this, okay, I think I'll just conclude here because I've gone fairly slow. But I'll just summarize here and say for the lab studies, we had strong evidence for pore condensation freezing, rendering deposition nucleation obsolete, we think. And then using the climate model, we saw that previous parameterizations will underestimate ice crystal number concentrations. In the field observations, the INP concentration difference that we saw was largely due to the aerosol size effect because that compensated for the differences between the different dust events. And we saw that pollutants could favor liquid phase ice formation compared to deposition mode. And then the Demotte parameterization described the data fairly well and suggested that aging of particles may not influence ice nucleation. And to come to the conclusions, to answer the two research questions that I postulated, is deposition nucleation real? Probably not for tropospherically relevant conditions and tropospherically relevant particles. Can we predict ice crystal number concentrations? We saw that we can predict the INP concentrations within a factor of 10. And this, I skipped over this, but in order to use INP to predict the ice crystal number concentrations, we need to consider other processes, which unfortunately I didn't get a chance to show you. But with that, I would like to thank you for your attention.
Okay, thank you, Zamin, for this nice presentation. And I think we have, tenemos un poquito de tiempo para algunas preguntas antes de irnos a ver el eclipse. Entonces,
we have 20 minutes still, I think.
20 minutes.
For the eclipse.
Entonces, ¿hay alguna pregunta para Zamin? Les pido el favor que cuando hagan las preguntas no le peguen al micrófono, dado que le van a estallar el oído a la traductora. Así que por favor no toquen el micrófono, ya están encendidos. Gracias.
Okay. My question is about you speak about the delay in the time of precipitation in polluted clouds and pristine clouds, but the enhanced of precipitation. What is the reason of the enhanced precipitation in polluted clouds?
Okay, so the enhanced precipitation, so you mean the delayed but enhanced precipitation, that should be because in a polluted cloud, so if you take this, you have many more droplets versus fewer droplets. So this would take a longer time to precipitate. And so the enhanced precipitation would come from the fact that you have more droplets, or in this case, more ice crystals, versus fewer droplets. So the density, precipitation density would be higher in this case. Yeah.
Okay, you have a question?
Dr. Kanji, I had the question about this very interesting phenomena of lyophilization. Some time ago, I was
Sorry,
involved
of
in
what was that?
lyophilization. That means condensation of, well, this phenomena that you described, that RHI sub I with RH sub W greater the sub I mean the ice against the wet water was very interesting to me, because I'm surprised that the lyophilization for water, it is best accomplished in the ice surface. It is a little different the results that I have. So my question is, there is something like in table of RH sub I against temperature, because it is very interesting. Well, it interests to me to compare with the material that I have. So there is something like that. There is another place in which you mention, and like uninterpreted humidity chart, that RH sub I against temperature. This is also very interesting, and there is some information about that, sir, doctor.
So is that you want to know if there's some information about that?
Well, if you have, there is some.
So you want to know if there's RHI versus temperature information?
Yeah.
Yes, of course. There is this very well-cited paper, at least in the atmospheric science, that's Murphy and Coop, 2005.
Yeah.
And that has a very comprehensive set of equations on how to calculate this, and gives you final derived equations for different temperature range validities. So you can calculate fairly accurately the partial pressure with respect to water and ice for a huge range of temperatures. So, of course, definitely. I can talk to you after, and I can even give you the paper right away. I can also give you my Excel tables because we use them very yeah.
Okay. ¿Alguna otra pregunta? La pueden hacer en español. Los estudiantes han estado muy callados, hasta donde yo recuerdo. Pueden hacerla en español y yo las traduzco.
Hola, ¿qué tal? Mi pregunta es si han tomado en cuenta bioaerosoles que promuevan también la nucleación del hielo, y si de alguna forma contribuyen también al proceso que ha descrito.
Okay, Luis will ever translate that.
I thought you know Spanish, no? So she's asking if how you consider or how you take into account bioaerosols and how they affect the processes that you have described here.
So that's a very good question. So the processes that I showed here today, I have not taken bioaerosols into account, or we have not taken bioaerosols into account. We can't exclude them from these results here, from the field results, because as you see that these are ambient particles. So I was just discussing earlier with some students that even in the desert you have biological particles. So these biological particles could be stuck onto these dust particles, so they're internally mixed. So it could be that in these results that I'm showing here, there is some influence of biological particles. But if it is the case, they are internally mixed with the dust. So the dust is acting as a carrier for them. So it is possible. The reason I don't believe there's such a strong influence is because we're doing these measurements at fairly cold temperatures, at -30 roughly. When we do the same measurements in the field at -20, we don't really see much. And biological particles, just from lab studies, are known to be active at warmer temperatures, so meaning between -5 and -15. And so if there were a lot of biological particles here, we'd probably see much higher ice nucleating particle number concentrations. So I don't think they influence these processes that I showed today. But we cannot completely exclude it. Yeah.
Hay una pregunta allá atrás, por favor.
Dr. Kanji, just a question. You made your studies with dust from the Sahara Desert. What about particles on top of the Amazon rainforest? And how does, because you showed a picture which is a very different atmospheric environment over South America. So how does it, or what do you think it might happen?
Yeah, that's a good question. So that goes back to this question of aerosol composition, or right, how different compositions will influence. Because over the Amazon, predominantly you'll have biogenic compounds. So probably you have SOA particles, organics, and so this would come. And people have studied organics, including myself, and people have done measurements in the Amazon for these particles. What we know from lab studies of organics is that, and Luis has also done some during his postdoc, is that they are active as ice nucleating particles, but at colder conditions. So we categorize them here after dust. So they tend to be active at conditions colder than -30. And so because some dust particles are even active at warmer conditions, we put them in this third category. So as far as ice nucleation is concerned, I think organics actually are found in ice crystals in the atmosphere. But when you have an environment where you're depleted in dust, so like the Amazon perhaps, in a non-dusty, not in the dry season, then the organics can become very important for ice nucleation or for ice cloud formation. Or if you consider to be in the Southern Ocean and you have a lot of marine influence and absence of dust, then the marine particles can become important. But when you have dust particles or biological particles present, together with organics, these probably nucleate ice in preference to the organics. So it depends on the atmosphere. So if you're directly above the Amazon and you're cold enough to freeze, probably you'll find a lot of organics in your ice. So that should play a role. And in fact, there's a lot of work done on that, showing that it can play a role in different mechanisms as well. Yeah.
Thank you. ¿Alguna otra pregunta? No? I do have a question. So you nicely showed that these pores play a big role, isn't it? So you said that when you implement the new parameterization in the model, it is a huge change, right?
Mm-hmm.
So by coming back to the question about bioaerosols, so do you think that we can find those pores in living organisms?
Yeah, I mean, I'm not a microbiologist, but I suspect that you could have these types of features in fungal spores or in biological particles. Whether these features can withstand the freezing process, because cells are softer, proteins are softer. So if the walls are made of proteins or cellulose, once you have the freezing process and expansion of ice, I think these walls could break or the pores could break. So I don't know if they would preserve their pore identity. And I think also because biological particles freeze at such warm conditions, you don't have this big gap between RHI and RH water. So you're always fairly close to water saturation conditions. That bulk water, you always have to consider bulk water or a bulk droplet. And so Whether biological particles will be relevant at cirrus conditions, I think that depends on their abundance in the atmosphere.
Okay, thank you. And I have a second question, and it's more regarding, I think it's Dr. Uribe's question, right? So you are over the Amazon. We know we are rich in organics, and we know we are rich in bioaerosols. So which one do you think are more important for ice clouds over the Amazon?
I mean, a very simple answer from lab studies would be bioaerosols. Because they just seem to be more active. They have more proteins that are ice nucleating proteins, so they just seem to be more active. I mean, the question is, if you're above the Amazon, which is a very ecologically active region, you have microorganisms and you have these SOA particles, probably. And the question is, can you really treat them mutually exclusive? Because I think they'll always be internally mixed. But if you were to do separate experiments, I think you would find the bioaerosols are more important. Keeping in mind that you need the bioaerosols to reach the atmosphere. And so the organics may just be merely carriers for the bioaerosols to reach the
Or they
ice
can
nucleating
code them.
conditions. Sorry?
Or they can coat the microorganisms with organics, no?
Yes, you can coat the microorganisms with the organics as well.
Okay.
And in that case, then the organic has to do the ice nucleation.
Yeah, and that's the problem. Then they have a large size, so they have a high deposition rate, so they might not make it that high.
Yeah.
Yeah.
But if you have fragments of microorganisms, right, you don't have to preserve the whole bacteria particle, the whole fungal spore, or the whole pollen particle to nucleate ice. Because a 20-micron particle is likely not going to have that much of a residence time, as you said. But the fragments that still release proteins and sugars can make it.
That's right. Okay, yo creo que ya está lo último. So thank you very much, Zamin, for being here.
Thank you for having me.